Here is Chapter 9, Section 1, problem number 15. Let's go through this one and get continued insight into this two-sample testing. In previous years, the average number of patients per hour at a hospital emergency room on weekends exceeded the average on weekdays by 6.3 visits per hour. A hospital administrator believes that the current weekend mean exceeds the weekday mean by fewer than 6.3 visits per hour. Okay, here the comparison, if just talk about this a minute, that 6.3 visits per hour, that's what our comparison is going to be. So we're looking at, is that difference of 6.3 the critical number we're thinking about here? So we'll come back to that in a few minutes because that's going to be part of our hypothesis test. Instead of it being 0, is it 6.3? Okay, A, construct the 99% confidence interval for the difference in the population means based on the following data. There's that table. Derived from a study in which 30 weekend and 30 weekday one-to-one periods were randomly selected and the number of new patients in each recorded. Okay, the randomly selected gives us the clue there that we're talking about this being independent, so they're done independently. So we've got the independence, and we've got that we can consider our sample size. Both of these are 30 or larger. So for both samples, we're in the area where we can utilize the central limit theorem for this being normally distributed. All right, so let's look at A here. We've got our 99% percent confidence interval. So our alpha is going to be 0.01. That's a goofy looking 99% there. Anyway, let's continue. So looking at that, we're going to be looking at a confidence interval on mu1 minus mu2. So on the difference between the means, we're going to be using sample means here because we don't have the actual mean of the populations because we have these two different populations, a weekend population and a weekday population. All right, so if we look at our notes and there in the chapter, we are looking at going from a confidence interval is going to be our difference in our means. And I'm just going to use these again as weekdays versus weekends, so 1 and 2. And you can use that either way, so that's just how you set it up, how you choose to use the 1 is the 1 and 1 is the 2. It works either way. Okay, so that difference in the means time plus or minus the z-value at our alpha over 2. So we're getting that in a minute, and then we've got the square root of our sample deviation and over the sample size plus the sample deviation. I forgot to say squared, I wrote it there. So sample deviation of the second sample squared over the sample size of that one. We looked at this there in number 13. Let's continue on with this example. So as we put numbers in, so we've got our 13.8 minus our 8.6. Boy, those 8s are just opposite each other. Plus or minus z at 0.01 over 2. And the square root of, let's see, 3.1 squared over 30 plus 2.7 squared over 30. The sample sizes are the same for both in this case. All right, let's continue looking at these and work these as we go through and make the subtraction. We're going to be in at 5.2 plus or minus. So this will be z of 0.01 or 0.005 because that's over 2 here. So z at 0.005, we can look that up in the t distribution at t at 0.005 at infinite degrees of freedom, because that gives us the same as the normal distribution in that case. And we look that up, that's that 2.576, and we have the square root of, okay, the 3.1 squared divided by 30 is 0.3203 plus the 2.7 squared over 30, which is 0.243. So we have 5.2 plus or minus 2.576 times that whole thing there turns out to be 7.50. So that's going to be 5.2 plus or minus 1.93. So our confidence interval is going to be 3.27 to 7.13. There we go for A. So that is our interval in which we're 99% confident that the difference in the means will land. And that's the smallest is 3, largest 7 approximately. So we know there is a difference. We're confident of that. Now, unfortunately, this interval that we're considered about, the one in the problem is the 6.3 visits, and we're between the 3 and 7 visits. So, it's starting to look like this is not going to be something that's going to be different. All right, so let's go into B. And B, we're going to test the significance at a 5% level of significance. So 5% is going to be, let me get rid of that equal sign there. So 5% level of significance means our alpha is going to be equal to 0.05. And so we're looking at whether the current mean exceeds the weekday by fewer than 6.3. So for our hypothesis testing, our null hypothesis is going to be that the difference in means, 1 minus mu2, so difference in means is going to be equal to our 6.3, and our alternative hypothesis is going to be mu1 minus mu2 is less than 6.3. So our initially looking there, the 6.3, that's going to be that D0, so the difference in the null hypothesis. That's that value we're looking at here that we'll look at here in the test statistic equation in just a moment. And so this thing is it going to be actually less than that? So the hospital administration is trying to determine have things changed and that it's not as big a difference between weekends and weekdays as it used to be, time-wise for the or actually number of patient-wise. All right, so step 1. This is essentially step 1 in our hypothesis, 5-step hypothesis testing process. So we have that one. Step 2 then is looking at determining what our test statistic is. And if we look at our test statistics, for this one we see that we actually have sample size large enough, and we're looking at the difference between our means of our sample sizes, and we're subtracting off the difference values. So sometimes this is 0 if we're looking at straight difference, but this one is how big that difference is. So in this case, that difference, the D0, is going to be our 6.3 that we had just talked about a moment before. And again, we have this whole value here of the sample size squared of each statistic added to each other. Not sample size squared, that's the sample deviation, the standard deviation, or sample deviation squared. There we go. And in this case, if we actually work this out, so this will be 2 and 3 together, because step 2 is determine the statistic, and step 3 is calculate it. So as we're calculating this one, we have our difference, which we calculated up above. So this difference here was calculated above, which is there. So we can get rid of those out of here to keep it from being too cluttered as we go through. There we go. So the difference, 5.2 minus our D, and we said our D, so the difference of in our null hypothesis was that 6.3. And that's going to be divided by this whole statistic, the square root jobber, which again, we calculated back up here, which turns out to be that 7.5. So let's pull that one back here. Don't need a smiley face under there. So this is divided by that 0.750. So this is going to be minus 1.1 over that 0.75. So minus 1.47 is what our test statistic value is. Give us a little more room here on the screen. And continue down. Step 4 then is actually determine the critical interval. So we're looking then, in this case, for our z for the one-tailed test, because we're looking at just being less than. So our z at our alpha is going to be z at 0.05. And it just so happens that that's not what we calculated up above there in part A. So this is a different confidence level. So we'll have to look up this z value. We look up that z at 0.05. Often easier to use the t-distribution for that, since we can get that read right off the distribution table there in the back of the book. And here this is minus 1.645. So essentially what we're saying there is our rejection interval is going to be from minus infinity up to minus 1.645. And we can see that our test statistic that we just calculated back in step 2 and 3, that z being minus 1.47, is not in the rejection region. Thus, in step 5 of our test for our hypothesis testing, we can see that we do not have statistical evidence at 5% level of significance. So we do not have it to reject, so we'll accept that the difference is not significantly below that 6.3 patients per hour. Continuing on to C. So C is compute the observed significance of the test. So our observed significance is the p-value of the test. So in our p-value here is looking at what's the probability value of our test statistic, and our test statistic was equal to minus 1.47. So the p-value, the probability value that gives us the test statistic of minus 1.47, we could go and just look at minus 1.47 of the cumulative normal distribution and look inside the table to come up with that value, what the probability for that is, and that winds up being 0.0708. So if we had looked at this as well, we can, from a p-value standpoint for the hypothesis testing, we could have said that at a p-value of 0.07, that's the probability of that actually happening is not less than the probability of our level of significance of 5%. So we don't have enough information or data that would say we would reject our null hypothesis. So we go forward with our null hypothesis is that we're still operating at the 6.3 patients per hour that we had previously. Okay.